So coming to the addressing mode supported for 16-bit data or signed byte data. 16-bit data we call it as half word. So with respect to load store instructions, the addressing modes supported for data transfer whose size is half word, that is 16-bit or signed byte. So what are the addressing modes supported? We'll see in this table. So what you can observe in this table is here scaled register offset is not there. So for these data types, that is half word, whether it is unsigned or signed, okay, and signed byte data and double word data. So if it were to be 64-bit data need to be transferred between the processor register and the memory. So actually that data type is supported in ARM version 5, where LDRD, where D stands for double word, where 64-bit data can be transferred. That instruction is supported in ARM version 5, LDRD and STRD. So what you have to remember here is, with respect to single register transfer, load store instruction, scaled register offset. So that addressing mode is not supported. Scaled means we'll be making use of barrel shifter operation. Hope you know that, right? Any of those 5 barrel shifter operations we can use if it were to be that is the scaled register offset, as we have seen in the previous class with respect to load store instructions for transferring 32-bit data or unsigned byte data. So one more addressing mode you had, that is scaled register offset. For scaling, we were using barrel shifter operation, right? But here, for these data types, that is unsigned half word or signed half word, signed byte or double word. So for these data types, that scaled register offset is not supported, meaning barrel shifter operation cannot be used for these data types, okay, with respect to load store instructions. So this is what you need to remember. The rest other is same. You can observe the addressing mode supported for earlier for pre-index, write back, and post-index. 3 addressing modes were supported, right? With immediate offset, register offset, scaled register offset. But here in this table, what you are seeing is scaled register offset is skipped. Excluding that, the other 2 addressing modes are supported. You can see pre-index immediate offset, pre-index register offset. With respect to pre-index write back, these are the 2 addressing modes supported. Pre-index write back, immediate offset, pre-index write back, register offset. Similarly, for post-index, the 2 addressing modes supported are immediate post-index, register post-index. So what you are observing, scaled register offset is not supported. So these operations where we are having half word, signed half word or signed byte or double word data transfer between the processor register and the memory, barrel shifter operation is not supported. That's why pre-index with scaled register offset, pre-index write back with scaled register offset, and scaled register post index. These 3 addressing modes are not supported for these data types. So this is what you need to remember. Okay. So rest other is same. Already you can see the addressing syntax. Syntax remains the same. Here earlier it was 12-bit offset where that was encoded in the machine code. Here it is 8-bit offset considered. And you can see within square brace, you are specifying the base address register, comma, you indicate if it were to be immediate offset, you are using hash symbol and you'll be specifying the offset, positive or negative offset. Similarly, for the second case, pre-index register offset, base address register, comma, you'll be specifying the register which holds the offset value. For the third addressing mode, pre-index write back immediate offset, you can see since it is write back, you'll be using not symbol here at the end in this expression. Within square brace, you are specifying base address register, comma, hash, immediate offset you are going to give. Followed by that, you are going to, once closing square brace is given, you are giving not symbol since the base address register need to be updated after performing the, that is once that instruction is executed. Similarly, pre-index write back with register offset. So the offset is residing in the register, one more register, RM. RN is the base address register. Within square brace, they are going to specify these 2 components, base address register, comma, that is the register which holds the offset. After that, you are going to give not symbol. Coming to immediate post index, where first we are going to take the current address held in the base address register. After accessing the data from that address held in the base address register, the base address register will be updated by whatever the offset you have specified in the instruction. So meaning remains the same. The only thing you need to notice, barrel shifter operations cannot be used for these data types, whatever listed in the table. that is half word, signed by, and double word. Okay, this is what you are seeing in the last column with respect to immediate post index and register post index. First, the base address register content is taken. You need to give comma and then the offset, which is to be added to the base address register to update the base address register. Similarly, the last one, register post index, you can see where the offset is residing in the register. After the base address register is specified, we are going to put comma and we will specify the register which holds the offset value. Okay. Coming to the examples, here earlier we had considered load instruction as examples for explaining the addressing modes, the 9 addressing modes supported for load, store, 32-bit data transfer and unsigned byte data transfer. Here for these addressing modes, that is what we have discussed in the previous slide. For that, we have considered STR instruction, that is STRH, half word, unsigned half word or 16-bit data transfer between the processor register and the memory. Okay, so STRH, where H stands for half word meaning 16-bit. Okay, unsigned 16-bit. And STR is actually, it can work for both unsigned and signed. If it were to be LDRH, then in that case it is unsigned. Since it is STR instruction we are dealing with, as we had already discussed in the previous classes, there is no STRH and STRSH instruction. The same STRH instruction can be used for writing 16-bit unsigned data to the memory or 16-bit signed data to the memory. For both unsigned and signed, STRH instruction is the only instruction which you can use. But for LDR instruction, there are two dedicated instructions. One is LDRH for unsigned data retrieval from the memory to the register, and LDRSH for retrieving the data which is interpreted as signed data, and that will be loaded to the processor register. So with respect to LDR, there are two instructions for retrieving or reading data, the 16-bit data from the memory to the register. For STR, for writing 16-bit data, there is only one instruction, that is STRH. Okay. Coming to this examples, already I think you have followed the instructions, the STRH instruction with the addressing mode. You can identify the addressing mode in the first instruction. It is pre-indexed with the write back. Once you see not symbol, you can easily tell it is write back, where the base address register is updated. Just see the last column, by what amount the base address register is updated. It is by 4, whatever the immediate offset you have given. So this is actually a pre-index write back with immediate offset. So you can see R1 is the base address register in these examples. Okay. In the second column, whatever the examples you are seeing for STRH instruction, in all these, it is R1 register. Okay. That is used as base address register. Uh, am I audible? Are you all following?
ma'am.
Yes, ma'am.
Okay. I thought I am on mute. Okay. Yes. See, R1 is the base address register, and you can see the updation done to the R1 register. If you are using immediate offset, R1 is equal to R1 plus that immediate value. This is the updation done. Since it is pre-index, first the address is updated, and then from that address, the data is, sorry, since it is STRH instruction, to that address, the data will be written. Whatever the data held in R0 register, that data will be written to the address. How that effective address is computed, base address register plus the offset, whatever specified in the instruction, these two will be added to at that address, the data will be written. Okay. Since it is half word, R0 register is a 32-bit register. You know, each register in ARM is 32-bit. Lower order 16-bit data will be taken, and that will be returned to the address computed. Okay, this is what you need to know. And you can see here the result. That's what I explained just now. In the third column, what you are seeing in this table is to where the data is written. So what is the address? See, mem16, 16-bit data is written to the address. How the address is computed? R1 plus 0x4, where 4 is the offset. So to the base address register, 4 is added. Whatever the effective address you get, to that address, R0 content will be written. Okay. In the same lines, you can analyze the rest of the instructions. STRH R0, comma, content of R1, comma, R2 not. So by what amount the base address register will be updated? Content of R1, content of R2 are taken, they are added. that updated address will be held in R1 register, and this is the effective address to where R0 register content will be written. Okay, it is updating. In first two examples, it is going to update the base address register, but it is pre-indexed, meaning first the address is updated. To that updated address, data will be written. Since and also it updates the base address register since not symbol is given. Pre-index means update the address first and then use that address to perform the operation. It may be the read or write operation. Write back means update the base address register. Hope these two words are clear. Pre-index, first update the address, then you go for using that address to perform read or write operation. If you are using pre-index with respect to str instruction, it is a write operation you are performing to the memory. Same addressing mode if you are using with respect to load, that is LDR instruction, LDRH, that means you are performing the read operation, okay, from that updated address. So pre-index, first update the address, write back. After updating the address, make the changes or modify this address in the base address register. That is the meaning. Okay. So just pre-index index method if you are using means it is not going to update the base address register. We can see the last column for third and fourth instruction. The base address register is not updated. Okay, but to calculate the effective address, it is going to take these two components. Base address register content is taken, 4 is added, and to this address R0 content is written. But this updated address will not be stored in the base address register. Okay, hope there is no confusion in the instructions. Similarly, the fourth instruction you can see, in the third instruction, it is immediate offset. So the addressing mode you can identify as pre-index with register, sorry, immediate offset. For fourth instruction, it is pre-index with register offset. Okay, totally it is 6 addressing modes. For single register transfer, load store instruction for loading or storing 32-bit data or unsigned byte data, it is 9 addressing modes supported. Okay, whereas here for half word, signed or unsigned, and signed byte and double word, for these data types, it is 6 addressing modes supported. So these are the 6 addressing modes. Pre-index write back with register immediate offset, pre-index write back with register offset, pre-index with immediate offset, pre-index with register offset, immediate post index, and register post index. As we are seeing in the last two instructions, strh r0 comma content of r1 comma hash 4, and the last instruction is strh r0 comma content of r1 comma r2, where you can see the offset is specified as an immediate data or offset may reside in a register. But if you are using post index, what is the meaning? You know the difference between pre-index and post index. In post index, first the current address held in the base address register is taken for accessing the memory. Then the base address register will be updated by whatever the offset you have specified. So that is the difference. Okay, you can see the third column for last two instructions. The content of R1 is taken. That is the effective address to where R0 register content is written. Okay. Similarly, for the last instruction, current address held in R1 is taken to write the data held in R0 to the memory. Then you can see the last column for the last two instructions. R1 register, which is the base address register, it is updated by 4, the immediate data, and the last instruction it is updated by R2. R1 equals R1 plus R2. So this is the updation done to the base address register. Okay. So just remember those points with respect to load store instruction, and this completes single register load store addressing modes and single register load store instructions, as well as addressing mode supported for single register load store instructions. Okay, now remember, for 32-bit as well as unsigned byte, 9 addressing modes are supported, 3 index methods are supported: pre-index, pre-index write back, and post-index. With respect to unsigned and signed half word and signed byte and double word, it is only 6 addressing modes supported, where the barrel shifter operation is not supported. That's why scaled register offset addressing mode for each of these indexing method is not used. Okay. So this is the summary which you can remember. Now we shall move on to the next type of load store instruction, that is multiple register load store instruction. So what do you mean by multiple register? Multiple register instruction. So single register instruction where single data item you can transfer between the processor register and the memory. Multiple register transfer instructions means you are able to transfer multiple data items. More than one data item we can transfer between the processor register and the memory. That is the meaning of multiple register transfer. See, load store multiple instructions. They can transfer multiple data items between the memory and the processor register in a single instruction. You can have one instruction to perform multiple register transfer. Okay, this is what the meaning. In case of a single register, what are the instructions? We had used LDR, STR instructions. Using LDR, STR instruction, only one data item we can transfer between the processor and the memory. Whereas using LDM, STM instruction, which is supported, where M stands for multiple. LDM, where it stands for load multiple. STM stands for store multiple. Okay, that means multiple data items we can transfer between the register and the memory using single instruction. So what are those instructions supported? It is LDM and STM. With syntax, we'll be discussing those two instructions. Okay. See, the multiple register transfer occurs from the memory address held in base address register. So whether you perform single register transfer or multiple register transfer, what is required is the starting address. Okay, from where the transfer has to take place or to where the data, multiple data is to be written. So starting address is to be specified in the instruction. So for that, we'll be making use of base address register. So in general, we call it as RN register. So multiple register transfer occurs from the memory address which is held in base address register. Coming to the applications of multiple register transfer instructions, so this we can say this multiple register transfer instructions are more efficient from single register transfer for these applications. So if you want to move block of data around the memory, so you're having some set of data, some bytes of data you're having in one block of the memory. So those bytes of data you want to transfer to another block of the memory. So block transfer, if you want to perform, you can go for multiple register transfer instructions. Or if you want to save and restore the context. So saving and restoring context means you assume you're having some valid data in the registers of the processor and you want to use the same registers to perform some other operation. So what you can do is you can save the current register status in the memory. You can use the registers to perform your operation. After completion of that operation, you want to restore back the register status by popping back or by retrieving back the data from the memory and write it back to the respective registers. So the saving and restoring of the context can be done using multiple register transfer instructions. So with example, I'll illustrate how we can save and restore the context. Okay. And one more application of multiple register transfer is stack. Okay, if possible, we'll try to cover first two applications of multiple register transfer, that is moving block of data around the memory and saving and restoring the context. Okay, in the coming class, we shall see stack, how to make use of this multiple register transfer instruction for push and pull operation of stack. Okay. And one small drawback with respect to load store multiple instruction is it can increase interrupt latency. If an meaning, what do you mean by interrupt latency? While we were discussing the pipeline execution characteristics of ARM7, what we discussed is even though interrupt occurs, the processor will not respond to that interrupt until the instruction which is in the execute state doesn't complete its execution. So this is what one of the pipeline execution characteristic which we have discussed. So if it were to be the load store multiple instruction that is being executed in the execute stage of the pipeline, in that case, since load store multiple means it is not just one register transfer taking place, it is multiple registers. This is an exceptional instruction, just recall, which takes more cycles for completing its execution. So that means even though interrupt has been raised, okay, by some external device, the processor cannot respond to that interrupt since in the execute stage, load store multiple instruction will be still in its completion of the execution. So only after it completes the execution, then only processor responds to that interrupt where the pipeline will be flushed off and the instruction from the ISR will be loaded to the pipeline and then it continues the execution. So with respect to load store multiple instruction, what you have to remember is it may increase interrupt latency. So interrupt latency meaning the delay. Interrupt is raised, but to respond to that interrupt, processor may take more time. So since LDM instruction or STM instruction, which is in the execute state, has to complete, once it is completed, then only processor is going to respond to the interrupt. Okay. So now we shall see the syntax of multiple register transfer instruction. LDM, STM, these are the two mnemonics supported. LDM stands for load multiple, STM stands for store multiple. And you can see, you can suffix the condition attribute for this LDM, STM instruction. Yes suffix should not be given, since it is not going to affect any of the flags, condition flags. And followed by that condition attribute, you have to specify the addressing mode. So see here, whatever you specify within flower brace, as I told, it is optional. So in all the syntax, what we have discussed with respect to the instruction set supported in ARM, what you have to remember is whatever we specify within pair of flower brace, it is optional to write in the instruction, but the rest others are compulsory. You have to specify the mnemonic, you have to specify the operands in the instruction. So with respect to load store multiple instructions, condition attribute is optional. Followed, if you are not giving condition attribute, that is fine, but you have to specify the addressing mode. Okay, then you need to give a space, then you have to give the base address register. So the first operand in load store multiple instruction is the base address register RN, and for that you can suffix not symbol. You know the meaning of not, whether to affect the base address register after execution of that LDM STM instruction, that depends on not symbol. If you're not giving that not symbol, then after execution, whatever the status you had before execution, the same status of the base address register you find after execution. Okay, so but if you give not symbol, then it is going to affect the base address register. Hope it is clear. Comma, you need to put comma, then the registers you need to specify as second operand. You need to give a pair of flower brace within which you will specify the list of registers which are to be used to perform multiple register transfer. So if some three register content you want to write to the memory, then you and if it were to be in sequence, if the registers are in sequence, say R1 to R3 registers, you want to use R1, R2 and R3. In that case, what you can do is within pair of flower base, you can specify R1 hyphen R3. So if it is in sequence the registers, you can simply give within flower base R1 hyphen R3. Hyphen symbol can be used to indicate the range of registers. Okay. But if it were to be distinct registers to be used for multiple register transfer, it may be load or store. In that case, you can separate each register by comma. So within flower brace, you'll write the registers which are to be used, each separated by comma. But if it were to be in sequence, the registers, then you can use hyphen to indicate the range of registers. Okay. Hope the syntax is clear. LDM, STM are the mnemonic supported for multiple register transfer. Condition attribute can be given for these instructions, but it is optional. Addressing modes are to be specified. So what are the four addressing modes supported that we'll see in the coming slides? RN is the base address register, which can be controlled, whether it can be, you can update it or you cannot update if you are giving not symbol. So if you're giving not, it is going to update. If you don't give, then it will not update the base address register after the execution of that instruction. And you need to put comma, then the list of registers you have to specify within flower brace, where the list can be the range of registers in sequence. If so, you can use hyphen. If it is not the range, the three distinct registers you want to use to perform the multiple register transfer, then you have to separate each register by comma. Okay. So what are the addressing modes supported for load store multiple instructions? It is these four addressing modes: IA, IB, DA and DB. See what this IA stands for? It is increment after. IB stands for increment before. Decrement after. Decrement before. So addressing modes, why we use addressing modes? Can anyone tell? Addressing modes. This is load store multiple instructions we are discussing. Addressing modes, what for it is used? What for addressing mode is used? Can anyone respond?
Ma'am, to modify the address.
Yes, to access the memory. The addressing modes, it is different ways of specifying the location from where the operand is to be fetched or to where the operand is to be written. Okay, to access the memory, we'll be using addressing mode. So, with respect to load, store, multiple instruction, it is these four addressing modes supported: increment after, increment before, decrement after, decrement before. Can anyone guess what may be the meaning? This is with respect, I'll give a hint. This is with respect to the base address register. Increment after. What is the meaning? Yes. Can you guess the meaning of these four addressing modes?
Post increment.
Very good. So first access whatever the address held in the base address register, take that address and then you increment. Okay, this is increment after. That means assume four registers you are using in the instruction, and that means four data word data are to be transferred between the processor memory and the processor register. In that case, so first whatever the address held in the base address register, that address is taken to fetch the data from the memory. Then the address will be updated. Whether first accessing takes place and then the address gets updated, or first address gets updated and then data will be accessed, so that depends on what addressing mode we are using. So increment after means first you access the data at the address held in the base address register, then update the address to fetch the next word in the memory. Okay, so increment before means first update the address, first increment the address, then go for fetching the data or write the data. Decrement after, so first go for fetching the data and then decrement the address. DADB stands for decrement after, decrement before, where after performing each word transfer, it is going to update the address. So either it will that is first it will fetch the data and then it will decrement the address, or it will first decrement the address and it fetches the data. Okay, so these are the four addressing mode. With examples, we'll be discussing each of these four addressing mode. IA, IB, DA, DB are the four addressing modes. If it is asked for multiple register transfer addressing modes supported in ARM, these are the four addressing modes you have to specify. If it is single register transfer, those 9 and 6 addressing modes you have to specify depending on what data type being asked in the question. Okay. So IA, IB, DA, DB, where I stands for increment, D stands for decrement, A stands for after, B stands for before. And this I already explained. Base address register RL, it determines the source or destination address for a load store multiple instruction. Okay, if it were to be that is the data fetch, it is the source. If it were to be STR instruction, STM instruction you are using, it is write operation, the destination address to where. So that means the starting address from where the data is to be fetched or to where the data is to be written, that is held in the base address register. And not symbol, which I already explained. If you want to update the base address register after execution of the instruction, you can use not character. So this is suffix to the base address register. Okay, and you can use any register in the register bank for performing this multiple register transfer. So that is the meaning of the last statement. Any subset of the current bank of registers can be transferred to the memory or fetched from the memory. Now coming to the addressing modes, the four addressing modes what we have listed. So these are the four addressing modes: IA, IB, DA, DB. This is the description you are seeing in the second column: increment after, increment before, decrement after and decrement before, and which block of memory will be accessed to fetch the data, to write the data. That starting and ending address is specified here with this expression. So if I say here, it may be difficult for you to understand. Let me take example for each of these addressing modes and let me explain with the illustration of the diagram. Okay, that in the coming slides we will be seeing. Just the meaning of starting address is the lower address. So some block, multiple register transfer are meant for block access, some sequence of memory you want to access. Okay, what is the lower address and higher address. Starting address means lower memory address, ending address means higher memory address. So this is how it is, the expression can be written for lower address and higher address, and by what amount the base address register will be updated. So that you are seeing here. So increment after execution of the instruction with increment after addressing mode, the base address register will be updated by Rn plus 4 into n. So after execution of IB instruction, it is the same. So whether you use IA or IB, before execution, whatever the Rn content you have, after execution, both will be updated by Rn plus 4 star n, where n is the number of registers you have used in the instruction for multiple register transfer. So if you are using 3 registers in the instruction, then whatever the current address you are having in the base address register plus 4 into 3. 4 into 3 is 12. So by 12, the base address register will be updated. It will be increased by 12. So similarly, increment before base address register, you can see the content by 12 will be added to the base address register. That will be the final address held in the base address register. So if it is increment after, increment before addressing mode, it is Rn plus 4 star n, the expression where n is the number of registers used in the instruction. If it is 3, each of these base address register will be updated by 12, 4 into 3. Okay. Similarly, here since each data, whatever you are dealing, it is 4 byte data. Okay. It is word data we are transferring. That's why it is 4 into number of registers you are using in the instruction. That's why it is 4. Okay. And for coming to the decrement after and decrement before instruction, see whatever the address held in the base address register, it will be decremented by 4 star n, where n is the number of registers. So all these expressions, the starting address, ending address, with example, I'll show in the coming slides. So remember the addressing mode supported, and remember by what amount the base address register will be updated, and what will be the block of memory, the starting address and ending address of accessing the locations. So that we'll see. One by one we shall see for each of those addressing modes. Let us take the precondition. These are the preconditions. See, 80018 is the memory location where 3 is stored, 14 it is 2, and 10 it is 1. And R0 is used as a base address register in the instruction. That's why I have highlighted with different color. 80010 is the address held in the base address register R0. And these are the register contents, other registers which are used in the instruction. So before execution of the instruction, this is the status of the register R1, R2 and R3. It is all 0. So before execution, this is the precondition diagrammatic representation for LDM-IA instruction. What is this LDM-IA? LDM stands for load multiple. IA is the addressing modes we have suffixed for the instruction. Increment after. That is the meaning. Okay. And you can see, as per the precondition what we have taken, R0 is a pointer to this memory 80010. You can see in the first column in this table, you are seeing the memory addresses, and in the second column, what you are seeing is the data stored at those addresses. Okay, this is the precondition we have considered as an example. Okay, 80010 is the starting address held in R0, which is a base address register. What is the data stored at 80010? It is 1. At 4, at 14, it is 2. At 18H, it is 3. At 1C, it is 4. And 20, it is 5. So some data is stored in the memory. And initial R1, R2, R3 contents are zeros. Okay. So now we shall consider the instruction. LDMIA are not, comma, you can see within flower brace we have specified R1 to R3. So if you want to specify the range of registers in sequence, you can use hyphen here. See, this is an example instruction for multiple register transfer. LDM is the mnemonic supported, IA is the addressing mode. So the complete mnemonic used is LDM IA. Okay, space, we are giving the first operand as the base address register. We have given not symbol. That means after execution of this instruction, base address register will get updated. The second operand is the list of registers you have given within pair of flower brace. Since it is in sequence, the registers R1, R2, R3, we have given hyphen and we have specified the registers. Okay. So once this instruction is executed, what will be the post condition? So LDM for, what is the meaning of LDM? Load multiple means we are reading multiple data item from the memory and we are going to transfer to these registers. This is fetching the data from the memory and writing to the processor registers. To which registers the data will be written? It is R1, R2, R3 registers in sequence. Okay. So how actually it fetches? The starting address is given 80010. So since it is increment after addressing mode use, what will be the content of R1 register? Can anyone guess the content of R1, R2 and R3? R0 is pointing to 80010. This is increment after addressing mode. We can easily tell, right?
R1 will hold 1, ma'am.
Yeah, very good. R1 holds 1. Then the pointer gets updated. It will be 80014. Okay. It fetches the next data at 80014 and that data will be returned to R2. 2 will be the value that will be returned to R2 and the pointer gets updated to 80018. From this location, it fetches the data 3 that will be returned to R3 register and then it updates the R0 register content. So what is the final address in R0? It will be 8001C. That will be the address. See, 8001C is the final address. After multiple register transfer is completed, the final address held in R0 will be 8001C. Just recall what I explained just now. Current address is taken. From this address, data is fetched. 1 is fetched, transferred to R1. Address gets updated. The next consecutive address is 80014. From where the next data is fetched, that is 2. It is transferred to R2 register. Then address gets updated. So what is the next address you will get? 80018. From this address, data is fetched. It is transferred to R3 and address gets updated. So these are the three registers we have used. So three memory access has been taken place. The final address in R0 will be 8001C. So if you are moving from lower memory address to higher memory address, okay, then whatever the first data you fetch from the memory, that will be transferred to the lower register. So nowhere it is explained in the in your instructions. So kindly note, data fetched usually will move from lower address to higher address or higher address to lower address. Whenever you are moving from lower address to higher address, whatever the data you fetch from the lower address, that will be stored in the lower register. The next data fetched will be stored in the next higher register, and so on. Okay, whatever the order you give for the registers here in the second operand. Okay, what I mean to say is, in the second operand, if you give R3, R2, R1, whatever the order you give for the registers R1, R2, R3, any order you give, in which order the data will be fetched. Okay, so each data fetched will be stored starting from the lower register. R1 is the lower register, then comes R2, then comes R3. So here you can observe, first data fetched, it will be transferred to R1 only. In any order you give the register, first data fetched will be stored in R1, second data fetched will be stored in R2, last data fetched will be stored in R3. So lower address data will be stored in the lower register, higher address data will be stored in the higher register. So whether you perform decrement or increment operation, remember this in general. Okay. See, R1, R2, R3, as you told, it is 1, 2, 3, the data that is fetched from the memory to these registers. So this is what the post condition you are seeing for LDM IA instruction. R0 is pointing to 8001C, the final address. Okay, but that location is not accessed. Only the pointer is pointing to this location. Which are the locations which are accessed to fetch the data? It is 80010, 80014, 80018. What is the starting address of the block which were fetched? What is the starting address? I want to discuss the expression. So that's why you please tell me. This was the starting address we had specified in the in the base address register 80010. You kindly tell me the starting and ending address of the locations which were accessed. Lower address, which is the lower address?
80010.
Yes, 80010 is the starting address. What is the ending address where the data is accessed?
80018.
80018, right? So 1C is the final address held in R0, but which are the locations that are accessed? 80010, 80014, and 80018. Only these three locations are accessed since we have used only three registers in the instruction. So just recall that table. In the previous slide, I showed one table with starting address, ending address, and updation done to the base address register. I have considered only for IA instruction since we are discussing an example with respect to IA instruction. Just see. AM means in short, just to simplify the expression, I've given IAM for addressing mode, DES for DESC for description, SA for starting address, EA for ending address, and RN is the base address register. IA is the addressing mode we are discussing. That means increment after. So what is the starting address? RN. What is the before execution of LDM IA? What was the content of R0? It is 80010. So what is the starting address from where the first data is fetched? It is 80010. Correct? RN. Whatever is there in RN, that is the location from where the first data is fetched. That's why starting address is RN. Hope this is clear. Okay. Coming to the ending address. So ending address is Rn plus 4 into Rn minus 4. 80010C is the location where R0 is pointing to. But what is the last location that is fetched? It is 80018. Yes or no? So what is the expression? Rn current address is 80010 plus 4 into n. How many registers transfer are taking place? It is 3 register transfer. So 10 means it is 16 in decimal. 16 plus 4 into 3 means it is 12. So 12 minus 4. What you'll get? It is 18. 80018. So this is the final address from where the data is fetched. Okay. So 12 minus 4 is, what is the value? 12 minus 4. 4 into n means 4 into 3, 12. 12 minus 4 means you will get 8. What is 10h plus 8? What is 10h plus 8? It is 18, right?
18H.
Yeah, 18h is the ending address. Hope the expression is clear. Starting address is whatever the address held in the base address register. Ending address is Rn plus 4n minus 4. So wherever Rn is pointing to, that minus 4. So you can see 4 and minus 4. That will be the ending address 80018 in our example, which is the address from where the last data is fetched in this memory. And by what amount the base address register is updated. See, Rn plus 4 into n. Rn is having 80010 plus 4 into 3 means 12. 12 means in hexadecimal it is C. So 80010 plus C means 8001C. This is the final address you are finding in R0 register. After execution of LDM IA instruction, this is the final address. Okay. Have you all followed? Are you able to understand? Followed? Any problem in
Yes,
understanding
ma'am.
this expression, starting address, ending address, and by what amount RN, the base address register is updated? Okay. Coming to the same thing I've explained here in LDM IA instruction in the example what we have discussed. R0 is used as a base address register and not symbol is given which updates the base address register. By what amount? It is Rn plus 4 into n, where n is the number of registers used in the instruction. Hyphen symbol can be used for a range of registers. In our example, we have used R1 to R3 with both registers inclusive. If you want to give the registers by separating with comma, that is also fine. We have to use pair of flower base anyway, and you have to separate each register with comma. And whatever the sequence of registers you give, always from lower register to higher register, the transfer takes place. Okay, if it were to be increment after addressing modules, lower address data will be stored in the lower register, higher address data will be stored in the higher register. Coming to the next example where IB addressing mode I've used, you can see this is the precondition. Just see the same data, whatever I've given in the precondition, same data I've represented diagrammatically here. 80010 is the address held in the base address register. Okay, and these are the data in these successive memory locations. Initially R1, R2, R3 contents are 0. Now tell me, after execution of this instruction, LDM IB R0 not, comma R1 to R3, what will be the contents of the registers and R0 pointer?
2, 3, 4.
Yeah, very good. 2, 3, 4. Since it is increment before, first it increments the address. What is the starting address from where the first data is fetched? It is 80014, right? Now, in general, what can be the expression? What can be the expression to for starting address? If Rn is the base address register, by what from which location first data is fetched?
Plus 4.
Plus 4. Are you getting? That is what the general expressions you are seeing in that table. So from first the first address from where data is fetched is the lower address. It is Rn plus 4. So 80010 is the address held in the pointer register, but 80014 is the first address from where the data is fetched. So just see the contents of R1, R2, R3. R1 is having 2, R2 is having 3, R3 is having 4. The final address, if we just compare IA and IB, the address held in the pointer register after execution of that instruction is same. So it is Rn plus 4 star n, where 4 is the value we are using, since it is each data is 4 byte and 3 registers are involved here. So whatever the address you are having in R0, that plus 4 into 3, 12. 12 means it is C. In both the examples, the final content of R0 remains the same. But what is the difference you are finding? In case of, in the previous example, what we have discussed, you can see in that example, let me go to that. See, where R0 is pointing to. So it is pointing the next location after the last data is fetched. Remember this. This is the main difference between IA and IB. In IA instruction, after completion of this execution, R0 pointer, it is pointing to the next location after the last data is fetched. Whereas in IB, where the pointer will be pointing to? In IB, increment before.
Same location of the last data fetch.
Yes, the location where the last data is fetched. Hope you got the difference. Good. Okay, that is what we need to identify with respect to LDM IA and LDM IB. See, 8001C, this is where R0 is pointing to. This is the last data that is fetched from the memory. This is the ending address, okay, from where the data is fetched. That's what I've listed here in this slide. After execution of LDM IB, R0 points to the last loaded memory in this IB instruction, whereas in case of LDM IA, it points to the next memory location after the last data is fetched. Okay, and you hope you have understood how in sequence the data is fetched and it is transferred to the registers R0, R1, sorry, R1, R2, and R3. And coming to the expression with respect to IB, okay, that is increment before. Starting address, as you told, Rn plus 4. Rn value we have taken is 80010 plus 4 means 80014. This is the starting address from where the first data is fetched, that is 2. It is transferred to R1 register. And the ending address, it is Rn plus 4 star n. Rn is 80010 plus 4 into 3, 12. So 10H plus C means it is 1C. That is what the final content you are seeing in R0 register. And the base address register, it is Rn plus 4n, same. So the base address register and the ending address, it is same, Rn plus 4 star n. Okay. Hope these two addressing modes you have followed, increment after and increment before for LDM. Okay. Shall we stop here? Have you all followed?
Yes, ma'am.
Okay.